Implementation of Relativity Space's 3D printing rocket technology by 2024. Introduction. Relativity Space, a trailblazer in aerospace manufacturing, is set to revolutionize the industry with its implementation of advanced 3D printing rocket technology by 2024. Central to this initiative is a strategic investment of $15 million aimed at enhancing production efficiency across the aerospace sector by an expected 30%. This report delves into the implications of this investment, the technology integration process, and the broader impact on the aerospace industry. The significance of the $15 million investment. The aerospace industry has long faced challenges related to complex supply chains, lengthy lead times, and high production costs. The $15 million investment by Relativity Space is a proactive step towards addressing these issues by enhancing advanced manufacturing processes. This investment is not merely a financial expenditure, it represents a significant commitment to innovation and efficiency. By channeling funds into 3D printing technology, Relativity Space aims to streamline the manufacturing of rocket components, which has been traditionally reliant on a multitude of parts and a complicated assembly process. The anticipated outcome of this investment is a substantial reduction in production time and costs, making it feasible to meet the increasing demands of the aerospace market. Technology integration and use cases. At the heart of Relativity Space's approach is the utilization of 3D printing to create large-scale rocket components. This technique allows for the production of intricate designs that conventional manufacturing methods struggle to achieve. Notable advancements include 1. Terran 1 rocket. This rocket serves as a prime example of how 3D printing can be leveraged to enhance production efficiencies. The Terran 1 incorporates a significant number of 3D printed parts, which reduces the need for assembly and minimizes material waste. 2. Material efficiency. Traditional manufacturing processes often result in excess material usage. In contrast, 3D printing enables a more precise approach, allowing for the creation of components that use only the necessary amount of material without compromising structural integrity. 3. Rapid prototyping. The ability to quickly iterate designs is a crucial advantage of 3D printing. This capability allows engineers to test and refine rocket components much faster than previously possible, thus accelerating the development cycle. 4. Customization. 3D printing facilitates the customization of parts for specific missions or payloads, providing aerospace companies with the flexibility to adapt designs to meet unique requirements. Sector-wide implications. The projected 30% increase in production efficiency is not just an isolated benefit for Relativity Space. This advancement could serve as a catalyst for a broader transformation within the aerospace industry. As other companies observe the successful implementation of 3D printing technologies and the resulting efficiencies, there is a strong likelihood that they will adopt similar manufacturing processes. Moreover, this shift towards advanced manufacturing could lead to a reduction in the overall costs associated with aerospace production, making space exploration and satellite deployment more accessible. The implications extend beyond cost. Improved efficiency can also lead to faster turnaround times, enabling companies to respond more swiftly to market demands. Common themes from various sources. Across different discussions surrounding Relativity Space's initiative, several themes emerge consistently. Transformative potential. The consensus is that 3D printing holds the potential to transform aerospace manufacturing. Enhanced efficiency, cost reduction, and the ability to iterate rapidly on designs are highlighted as key benefits. Strategic positioning. The investment represents a strategic move for Relativity Space to establish itself as a leader in the evolving aerospace technology landscape. By pioneering the integration of 3D printing into rocket manufacturing, the company positions itself at the forefront of innovation. Differing perspectives. While the majority of sources project a positive outlook on the implementation of 3D printing in aerospace, some express skepticism regarding its scalability. Concerns revolve around the reliability of 3D printed components in extreme environments that rockets often encounter. Critics argue that until comprehensive testing validates the durability and performance of these components under harsh conditions, the technology may not be fully embraced by all sectors of the aerospace industry. Timeline of events. Early 2020s, Relativity Space initiates the development of its 3D printing technology, emphasizing the need for fewer parts and materials in rocket manufacturing. 2023, the company secures the pivotal $15 million investment to expedite the advancement of its manufacturing processes and significantly enhance production efficiency. 2024, the anticipated rollout of the 3D printing technology is planned, with expectations to yield rockets that are produced more efficiently and cost-effectively. Conclusion. Relativity Space's ambition to implement 3D printing technology for rocket manufacturing by 2024 signifies a monumental shift in aerospace production methodologies. By focusing on efficiency and innovation, this initiative is poised to redefine manufacturing standards within the industry. Despite differing opinions regarding the long-term viability of 3D printed components in extreme aerospace conditions, the potential benefits of enhanced production efficiency and reduced costs make this investment a pivotal development. As the aerospace sector continues to evolve, the implications of Relativity Space's innovations could pave the way for a new era of manufacturing and space exploration and beyond. The content presents a detailed overview of Relativity Space's initiative to implement 3D printing technology in rocket manufacturing by 2024. Backed by a $15 million investment aimed at enhancing production efficiency across the aerospace sector. While the summary highlights the anticipated benefits of this technology, several counterintuitive aspects emerge upon deeper analysis. 1. Perception of 3D printing versus traditional manufacturing. One might assume that the aerospace industry, known for its rigorous standards and safety protocols, would be hesitant to adopt a cutting-edge technology like 3D printing. However, the investment and push for implementation suggest a significant shift in this perception. The traditional view is that aerospace components require extensive testing and validation due to the extreme conditions they face. The counterintuitive aspect here is that despite these concerns, the industry is willing to embrace 3D printing as a viable alternative, indicating a growing confidence in the technology's ability to meet stringent requirements. 2. Efficiency versus reliability. The projected 30% increase in production efficiency may seem straightforward, implying that 3D printing will universally streamline production. However, this overlooks the potential trade-offs in reliability and quality assurance. The aerospace sector places a premium on reliability, and the shift to 3D printing raises questions about the robustness of printed components, particularly in high-stress environments. This counters the assumption that increased efficiency inherently equates to improved overall performance in aerospace manufacturing. 3. Investment in industry benchmarking. The decision to invest $15 million in 3D printing technology could be viewed as a strategic risk given the skepticism surrounding the scalability of such technologies. While one might expect companies to take a conservative approach in a high-stakes industry, Relativity Space is positioning itself as a pioneer. The counterintuitive notion is that by taking on this risk, they could set a new benchmark for the industry, encouraging others to follow suit despite potential initial setbacks. For material waste reduction, a common assumption about 3D printing is that it inherently reduces material waste due to its additive nature. However, the reality is more complex. Certain 3D printing processes can lead to waste in different forms, such as failed prints or the need for post-processing. This contrasts with traditional subtractive manufacturing methods where waste is often more predictable. The claim that 3D printing will reduce material waste may not hold true universally across all applications within aerospace manufacturing. 5. Design flexibility versus production complexity. The narrative emphasizes design flexibility as a key advantage of 3D printing, yet this can lead to increased complexity in production. While the ability to create intricate designs is beneficial, it can also complicate the manufacturing process, requiring more advanced control systems and quality checks. This challenges the assumption that greater design freedom will straightforwardly lead to simpler or more efficient production. 6. Scalability concerns. While the technology promises efficiency gains, there is skepticism about its scalability in large-scale production. The counterintuitive element here is that while 3D printing can facilitate rapid prototyping and small batch production, effectively scaling up to mass production levels may introduce new challenges such as maintaining consistent quality and managing production timelines. This contrasts with the assumption that once technology is proven at a smaller scale, it can be seamlessly transitioned to larger scale operations. 7. Market dynamics and competitive advantage. The analysis implies that other companies in the aerospace sector will likely adopt similar technologies, creating a competitive landscape that could diminish Relativity Space's first-mover advantage. This counters the expectation that being an early adopter guarantees market leadership, as increased competition may erode the initial benefits of technological innovation. 8. Public perception and acceptance. The general public and industry stakeholders may have differing views on the adoption of 3D printing in aerospace. While industry insiders may recognize the potential efficiencies, the broader public might remain skeptical about the safety and reliability of 3D printed components. This divide challenges the notion that technological advancements will be uniformly embraced across all sectors. In conclusion, while the initiative by Relativity Space to implement 3D printing technology promises numerous advantages, the underlying complexities reveal counterintuitive insights that challenge conventional assumptions about manufacturing efficiency, reliability, and industry dynamics. The interplay between innovation and traditional aerospace manufacturing standards will likely shape the future landscape of the sector in unexpected ways. The report on Relativity Space's implementation of 3D printing rocket technology by 2024, backed by a $15 million investment, highlights several critical aspects that are significant yet may be overlooked by many readers. Here are the key overlooked points and their significance. 1. Cultural shift in manufacturing mindset. While the report emphasizes efficiency and cost reductions, it fails to address the broader cultural implications of adopting 3D printing in aerospace. The traditional aerospace industry is characterized by long lead times, extensive testing, and a conservative approach to material and design changes. The shift to 3D printing represents not just a technological change but a profound cultural shift towards rapid prototyping, agile manufacturing, and a willingness to embrace iterative design processes. This cultural transformation could lead to more innovative solutions and a more dynamic industry. Significance. Understanding this cultural shift is crucial because it can influence how companies approach product development and risk management. Organizations that adapt to this new mindset may find themselves better equipped to respond to market demands and technological advancements. 2. Environmental considerations. The report mentions reduced material waste as a benefit of 3D printing but does not elaborate on the environmental impact. The aerospace industry is under increasing pressure to reduce its carbon footprint, and the ability to manufacture components more sustainably can significantly enhance a company's public image and comply with regulatory requirements. Significance. Companies that prioritize sustainability in their manufacturing processes could gain a competitive advantage as consumers and regulators increasingly favor environmentally friendly practices. This aspect of 3D printing could attract investment and partnerships focused on green technology. 3. Customization and design freedom. The report highlights the ability of 3D printing to produce complex designs but does not fully explore the implications of customization capabilities. 3D printing allows for the rapid production of tailored components, which can lead to enhanced performance and efficiency in rocket designs. This level of customization can also enable smaller companies to compete with larger manufacturers by providing niche products that meet specific customer needs. Significance. The potential for customization may disrupt the traditional supply chain dynamics in aerospace, allowing for smaller entrants to thrive and innovate. This could lead to a more diverse range of products and services in the market, fostering competition and innovation. 4. Interdisciplinary collaboration. The report does not address the need for interdisciplinary collaboration that 3D printing encourages. The integration of technology across various fields, such as materials science, engineering, and software development, will be essential for maximizing the potential of 3D printing in aerospace. Significance. Encouraging collaboration among different disciplines can lead to breakthroughs in material properties and design techniques, enhancing the overall capabilities of the aerospace industry. This collaborative approach can also attract a more diverse talent pool, contributing to a richer innovation ecosystem. 5. Long-term viability and reliability concerns. The report mentions skepticism regarding the scalability and reliability of 3D printed components in aerospace applications, but does not delve into how these challenges might be addressed. The aerospace sector has stringent safety and reliability standards, and ensuring that 3D printed parts can meet these requirements is paramount. Significance. Addressing concerns about reliability and scalability is critical for broader industry adoption. The development of rigorous testing protocols and standards for 3D printed components could facilitate market acceptance and encourage larger aerospace firms to invest in similar technologies. 6. Regulatory and compliance challenges. The report lacks a discussion on the regulatory landscape surrounding the use of 3D printing in aerospace. The aerospace industry is heavily regulated, and navigating these regulations can pose significant challenges for companies looking to implement new manufacturing technologies. Significance. Understanding regulatory challenges is essential for successful implementation. Companies must proactively engage with regulators to ensure compliance, which could influence the pace of adoption and the design of new technologies. 7. Economic impact beyond aerospace. While the report focuses on the aerospace sector, it overlooks the broader economic implications of increased efficiency through 3D printing. The aerospace industry often serves as a bellwether for advanced manufacturing technologies, and innovations in this sector can have ripple effects across various industries, including automotive, defense, and consumer goods. Significance. Recognizing the broader economic impact of aerospace advancements can help justify investments in 3D printing technologies, as benefits may extend beyond the aerospace sector and stimulate economic growth and job creation in related fields. Conclusion. Relativity Space's initiative to implement 3D printing technology in rocket manufacturing by 2024 is not just a technical advancement. It represents a shift in manufacturing philosophy, sustainability practices, and industry dynamics. By recognizing and addressing the overlooked aspects of cultural shifts, environmental considerations, customization, interdisciplinary collaboration, reliability, regulatory challenges, and economic implications, stakeholders can better understand the full potential of this transformative technology in the aerospace sector and beyond. 1. Investment in advanced manufacturing processes. The $15 million investment by Relativity Space is crucial for advancing aerospace manufacturing. This financial commitment not only indicates confidence in 3D printing technology but also serves as a catalyst for innovation within the industry. By enhancing manufacturing processes, this investment aims to address long-standing challenges like lengthy lead times and complex supply chains. This point can be further analyzed in terms of the potential return on investment, the impact on job creation within the manufacturing sector, and how this financial backing aligns with broader trends in aerospace and technology investments. 2. Revolutionary technology integration. Relativity Space's use of 3D printing for large rocket components marks a significant shift in manufacturing methods. The ability to create intricate designs that are cost-effective and time-efficient could disrupt traditional aerospace manufacturing practices. An in-depth discussion could focus on the specifics of the 3D printing technology being employed, including materials used and the precision of the printing process. Additionally, the implications of reduced material waste and the potential for rapid prototyping and iterative design processes could be explored, emphasizing how these capabilities can lead to innovative design solutions. 3. Sector-wide implications and adoption. The expected 30% improvement in production efficiency is not just a win for Relativity Space, it has the potential to set a benchmark for the entire aerospace sector. The ripple effects of this advancement could prompt other aerospace companies to invest in similar technologies, leading to a broader industry transformation. An analysis of how this could influence competitive dynamics within the aerospace sector, as well as the integration of 3D printing across various aerospace applications, e.g. satellites, drones, would provide valuable insights. Future scenarios could be drawn to illustrate how early adopters might gain market advantages over traditional manufacturers. For skepticism and reliability concerns, despite the promising outlook for 3D printing in aerospace manufacturing, there remains skepticism regarding the scalability and reliability of 3D printed components under extreme conditions. An in-depth examination of this skepticism could include case studies of past failures or challenges in the adoption of new technologies in aerospace. Evaluating the regulatory environment, testing standards, and certification processes required for 3D printed components could provide a comprehensive understanding of the hurdles that must be overcome for widespread acceptance. This discussion could also encompass the balance between innovation and safety, a crucial aspect of aerospace engineering. These 4 points provide a framework for a thorough analysis and discussion regarding the implementation of Relativity Space's 3D printing rocket technology and its implications for the aerospace industry as a whole. Here are 3 famous historical cases that are similar in nature to the implementation of Relativity Space's 3D printing rocket technology and its impact on production efficiency in the aerospace sector. 1. The Apollo program and the advancements in aerospace manufacturing. The Apollo program, which took place between 1961 and 1972, was a pivotal moment in space exploration history. Spearheaded by NASA, the Apollo missions aimed to land humans on the Moon and return them safely to Earth. The program necessitated significant advancements in manufacturing and technology, particularly in the development and production of the Saturn V rocket. The Saturn V was a marvel of engineering composed of more than 3 million parts and required extensive coordination within the aerospace supply chain. The program's demands resulted in innovations in materials science, production techniques, and quality assurance processes. The integration of new manufacturing technologies such as automated welding and high-precision machining significantly reduced production times and improved reliability. The lessons learned from the Apollo program continue to resonate in modern aerospace endeavors, including the current push toward additive manufacturing and 3D printing technologies. Just as Apollo set new standards for efficiency and capability in rocket manufacturing, Relativity Space seeks to redefine production methodologies through its investment in 3D printing. 2. The development of the Boeing 787 Dreamliner. The Boeing 787 Dreamliner, introduced in 2011, is another significant case that showcases the evolution of manufacturing techniques in the aerospace industry. The Dreamliner was notable for its use of composite materials and its innovative manufacturing processes, which included global outsourcing and modular assembly. Boeing invested heavily in advanced manufacturing technologies to produce the 787, leading to a more efficient assembly line that aimed to reduce production time and costs while enhancing aircraft performance. The 787's production utilized a significant number of parts manufactured using advanced techniques, including composites that are lighter and more fuel efficient than traditional materials. However, the project faced its challenges, including delays and quality control issues, which highlighted the complexities of integrating new technologies across a global supply chain. Despite these hurdles, the lessons learned from the 787 program have fueled ongoing advancements in aerospace manufacturing similar to the potential impacts of 3D printing on the industry as envisioned by Relativity Space. 3. The introduction of lean manufacturing in the automotive industry. The adoption of lean manufacturing principles, most notably by Toyota in the 1950s and 1960s, transformed the automotive industry and provided a blueprint for efficiency that has been emulated across various sectors including aerospace. Lean manufacturing focuses on minimizing waste while maximizing productivity, leading to significant improvements in production processes. Toyota's implementation of lean principles, including just-in-time JIT production and continuous improvement Kaizen, allowed the company to respond rapidly to market demands while maintaining high-quality standards. These practices resulted in shorter production times and reduced inventory costs, revolutionizing the way vehicles were manufactured. The aerospace industry has since drawn inspiration from lean manufacturing techniques to streamline processes and enhance production efficiency. As Relativity Space seeks to apply 3D printing technology to achieve similar efficiency gains, it is building on a rich history of innovation in manufacturing that has roots in successful transformations like those seen in the automotive sector. Conclusion. Each of these historical cases, the Apollo program, the Boeing 787 Dreamliner, and the rise of lean manufacturing, illustrates the transformative impact that innovative manufacturing processes can have on the aerospace industry. As Relativity Space embarks on its journey to integrate 3D printing technology into rocket manufacturing, it stands on the shoulders of giants looking to enhance production efficiency and redefine standards in aerospace engineering. Future outlook. Predictions for the implementation of Relativity Space's 3D printing rocket technology by 2024. As we approach 2024, the aerospace industry is on the brink of a transformative shift due to the implementation of Relativity Space's 3D printing rocket technology. The $15 million investment in advanced manufacturing processes is expected not only to enhance production efficiency by 30% but also to redefine how rockets are designed, manufactured, and launched. Here are the key predictions regarding this initiative and its broader implications for the aerospace sector and beyond. 1. Accelerated production timelines. By 2024, it is anticipated that the integration of 3D printing technology will significantly shorten the timelines required for rocket production. Traditional manufacturing methods involve lengthy procurement processes for parts and components, resulting in extended lead times. With 3D printing, Relativity Space is expected to streamline production, enabling faster turnaround from design to deployment. This could lead to reduced waiting periods for satellite launches and increased frequency of missions, thereby enhancing the overall competitiveness of launch providers. 2. Cost reduction and economic viability. The expected 30% increase in production efficiency will likely translate into substantial cost savings. As components become cheaper to produce, the overall cost of launching rockets may decrease, making space access more economically viable for a broader range of customers, including startups and international space agencies. This democratization of space access could foster innovation and growth in the space economy, encouraging new players to enter the market. 3. Design innovation and customization. 3D printing allows for more complex and customized designs that were previously impractical or impossible with traditional manufacturing techniques. By 2024, we can expect to see a rise in innovative rocket designs enabling tailored solutions for specific missions or payloads. This capability will not only enhance mission performance but also provide a competitive advantage to companies that can quickly adapt their designs based on changing market demands. 4. Sustainability in aerospace manufacturing. The shift towards 3D printing technology also aligns with growing sustainability concerns within the aerospace industry. The reduction of material waste and the potential for using eco-friendly materials are expected to become key selling points for companies employing this technology. This focus on sustainability will likely resonate with stakeholders including government agencies and private investors, who are increasingly prioritizing environmentally responsible practices. 5. Industry-wide adoption and benchmarking. As Relativity Space demonstrates the effectiveness of its 3D printing technology, other aerospace companies may follow suit, leading to a widespread adoption of similar manufacturing processes. This trend could establish new benchmarks within the industry, driving competitors to innovate and enhance their manufacturing capabilities. The ripple effect could result in a collective push towards advanced manufacturing technologies, thereby transforming the aerospace supply chain. 6. Challenges and skepticism. Despite the optimistic predictions, challenges remain. The debate over the scalability and reliability of 3D printed components in high-stakes aerospace applications is likely to persist. By 2024, as Relativity Space initiates its technology implementation, it will need to address these concerns through rigorous testing and validation of its components. Building trust in the reliability of 3D printed parts will be critical for wider acceptance and adoption across the industry. 7. Collaboration and partnerships. The implementation of advanced manufacturing processes may also foster new collaborations and partnerships within the aerospace sector. As companies recognize the potential of 3D printing, we may see increased joint ventures between manufacturers, technology providers, and research institutions to explore and enhance these capabilities. Such collaborations could accelerate innovation and facilitate knowledge sharing, further pushing the boundaries of what's possible in aerospace manufacturing. Conclusion: a new era in aerospace. The implementation of Relativity Space's 3D printing rocket technology by 2024 is anticipated to herald a new era in aerospace manufacturing. With an emphasis on efficiency, cost reduction, and sustainability, this initiative is set to revolutionize the industry. As the effects of this technology unfold, the aerospace sector will likely experience increased competition, innovation, and collaboration, leading to a more dynamic and accessible space economy. The coming years will be critical as stakeholders navigate the challenges and opportunities presented by this technological advancement, shaping the future landscape of aerospace for decades to come.